Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It is great to be here.
Today, we are exploring the architecture of uncertainty. And I have to be honest, when I started digging into the sources for today, I felt this sort of creeping dread.
Dread. That's a strong word to start with.
Well, think about it. Our entire lives, our entire society, is built on the idea of prediction. We check the weather, we follow stock market projections, we plan our careers. We are obsessed with knowing what's coming next.
Right. It gives us a sense of control.
Exactly.
Yeah.
But the material we're looking at today, it basically suggests that sense of control is an illusion. And not just a small illusion, a fundamental one.
It's a huge reality check, isn't it? We have this baked-in assumption that if we just had a little more data or a faster computer, the future would eventually become open book.
Yeah, that the fog would lift.
But the research argues that the fog isn't just because our eyesight is bad. The fog is a structural feature of the universe. It's built into the physics.
It's not a bug, it's a feature. I think that's the phrase that kept ringing in my head. We're not talking about missing a few data points. We are talking about, hard limits, walls built into the very laws of logic and nature that say you cannot know what comes next.
Exactly. And to really feel the weight of that, we have to start with the dream that it shattered. We have to go back to the 19th century. We have to talk about something called Laplace's demon.
I love that name. It sounds so dramatic. It's not a literal demon, though, is it?
No. It's a thought experiment from Pierre-Simon Laplace, a brilliant French scholar in the early 1800s. He imagined a vast intellect. He didn't actually call it a demon, that came later. But he pictured this being that, for one single instant, knew the exact position and momentum of every particle in the universe.
Okay, so like a cosmic snapshot. It freezes time and knows where every atom in this microphone is, every molecule of air, every star in every galaxy.
A perfect, infinitely detailed snapshot. And Laplace's argument was this. If that intellect also knew all the physical laws that govern those particles, gravity, motion, everything, then for that intellect, nothing would be uncertain, and the future, as the past, would be present to its eyes.
That is such a profound and honestly a terrifying idea.
It is.
It implies a completely clockwork universe, that everything is just gears turning, that the future is already written, and if you're smart enough, you can read the script.
It's the ultimate statement of scientific determinism. No free will, no chance, just cause and effect playing out on a cosmic scale. The Big Bang was the first push of the dominoes, and everything since you and I having this conversation right now was inevitable.
That dream is dead. We know it's dead, otherwise our lives would be completely different. So the story of the last 100 years, and really the story we're exploring today, is the systematic execution of that demon.
The demon is buried. And what killed it wasn't a lack of trying. It was the slow dawning discovery that the universe is, to use a fantastic term from our research, epistemically opaque.
Epistemically opaque. That's a very academic way of saying we're flying blind.
It's a little more nuanced. It means that even if the universe is deterministic, even if cause and effect is all there is, that doesn't make it predictable for us. There are walls between what is true and what we can know.
And that's our mission today. We're going to map out those walls. We'll start with the foundations, the core reasons the clockwork universe fell apart. Then we'll dive into an active debate that's happening right now. Are huge disasters like market crashes, random black swans, or predictable dragon kings?
After that, we'll look at the frontiers. We're talking quantum computing, AI, the technologies that promise to push back the fog, but might just create new kinds of uncertainty.
And finally, we'll get into the implications. What does all this mean for the economy, for social justice, even for warfare? It gets very real very fast.
It really does.
So let's start at the beginning. Section 1, foundations. What we think we know, or maybe what we now know we don't know.
Let's start taking that clock apart.
Okay, so the first big idea that really reset my thinking was this distinction the research makes between determinism and predictability. I, like most people I think, use those words interchangeably.
It's a very common confusion, and it's the first major crack in the Laplacian worldview. So determinism is simple. It just means that the current state of a system is the sole cause of the next state. A leads to B. No magic, no randomness injected from the outside.
So the laws of physics are consistent. If I drop this pen, it will fall.
Yeah.
Every time. That's determinism.
Exactly. But predictability is about something else entirely. It's about whether we, as observers inside this universe, with our limited brains and our finite computers, can actually calculate what B will be before it happens.
And the answer is, sometimes we can.
Sometimes we can't, even in systems that are perfectly deterministic. And that brings us to this fantastic concept called computational irreducibility.
It's a bit of a mouthful.
It is, but the idea behind it is actually pretty simple once you get it. It comes from Stephen Wolfram. Imagine you have a complex system, like the weather, or even one of his cellular automata, which are just grids of pixels that follow simple rules.
Okay.
To find out what that system will look like a million steps from now, there's often no shortcut. You can't just plug the starting conditions into a neat little formula and get the answer.
So there's no FXY for the future.
Precisely. The only way to know the future state of the system is to actually run the system. You have to compute step 1, then use that result to compute step 2, then step 3, and so on for a million steps.
You have to watch the whole movie. You can't just skip to the end.
You can't. The most efficient simulation of the system is the system itself. Its evolution is irreducible. You can't reduce it to a simpler calculation.
Okay, so what does that mean for prediction? If I want to predict the weather a month from now?
You have to build a computer simulation of the atmosphere and let it run for a month's worth of simulated time.
But what if that simulation, because it's so complex, takes a real month to run on my supercomputer?
Then you haven't predicted anything, have you? You've just described what happened at the same speed it happened. Your prediction arrives at the exact same time as the reality. Useless.
Wow. So that's the first wall. The universe just doesn't allow us to fast forward some processes. It forces us to be patient and watch them unfold.
It's a fundamental speed limit on knowledge. But that's just the start. The second wall is far more famous. It's the one that really brings the idea of uncertainty into the mainstream. Deterministic chaos.
The butterfly effect.
The butterfly effect. Everyone's heard the phrase, but the story of its discovery is, I think, really telling. We have to go to the 1960s to an MIT meteorologist named Edward Lorenz.
Right. He was one of the first people trying to model the weather on a computer, a very, very primitive computer by today's standards.
Barely more than a calculator. He had this program that simulated a dozen variables for weather temperature, pressure, wind speed. And one day, he wanted to rerun a sequence to look at it more closely.
Instead of starting the whole simulation over from the beginning, he decided to start it from the middle, right?
Exactly. A total time saver. He had a printout of the data from the previous run. He looked at the numbers on the page and typed them back into the machine to restart the simulation from that point.
Seems perfectly logical.
Here's the catch. His computer, in its internal memory, stored the numbers with 6 decimal places of precision. For example, 0.506127.
Okay, very precise.
But the printout, just to save space, rounded those numbers off to 3 decimal places. So it just said 0.506.
So he was off by an absolutely minuscule amount, 1,000th of a decimal point. It's like measuring the distance from here to the moon and being off by a few feet. You wouldn't think it would matter.
He certainly didn't. He typed in the rounded numbers, started the program, and went down the hall to get a cup of coffee. He expected that when he came back, the new simulation would be tracing the exact same path as the old one.
But it wasn't.
Not even close. For the first little while, the two simulations tracked each other. But then they started to diverge. And then they diverged wildly. After a few simulated months, the weather patterns were completely unrecognizably different. That tiny, insignificant rounding error had been amplified by the system until it changed everything.
And that's the butterfly. The idea that a butterfly flapping its wings in Brazil, a tiny perturbation in the atmosphere, could, weeks later, cause a tornado in Texas.
But we need to go deeper than the metaphor. The research points to the math behind this, and it's a concept called the Lyapunov exponent.
Right. I saw that in the notes. Let's really unpack this because it sounds intimidating, but it's at the heart of everything. What is it actually measuring?
The best analogy is to think of 2 leaves dropped into a stream. Imagine the stream is very slow and smooth, what physicists call laminar flow. You drop the 2 leaves right next to each other, almost touching.
Okay, I can picture it. They just float along together.
Pretty much. The distance between them might grow a little bit, but it grows linearly, slowly and predictably. If you know where one is, you have a very good idea of where the other is.
Right.
Now imagine the stream is a raging torrent full of rapids and eddies. It's turbulent, it's chaotic. You drop those 2 leaves in the exact same spot again.
They're gone. One gets whipped into a whirlpool, the other shoots off to the side.
In seconds, they could be 100 feet apart. The Lyapunov exponent is the mathematical measure of that rate of separation. If the exponent is positive, it means that the distance between those two leaves grows exponentially.
It doesn't just add, it multiplies, it doubles, then doubles again, then doubles again.
Precisely. Now apply that to prediction. One of those leaves is the true state of the atmosphere, the actual real weather.
And the other leaf is our best measurement of it.
Yes, and no matter how good our satellites and weather balloons are, there is always a tiny gap between reality and our measurement. It might be a tenth of a degree, a tiny shift in wind speed, a microscopic error.
And because the atmosphere is a chaotic system with a positive Lyapunov exponent.
That microscopic error explodes. It gets amplified by the system, doubling and redoubling. This leads to something called the Lyapunov time. It's the time scale on which a system becomes unpredictable. It's the prediction horizon.
And for weather, the research says that's about 2 weeks. Is that a hard limit?
It appears to be a hard mathematical limit. It's not a technology problem. It doesn't matter if we have a quantum computer the size of a planet. The inherent chaos of the system means that after about 14 days, the initial tiny error will have grown so large that our forecast is no better than a random guess.
That's genuinely humbling. It's not that we're not smart enough. The universe itself has a no trespassing sign on the future past a certain point.
And it gets worse.
Of course it does.
Because the butterfly effect is all about sensitivity to initial conditions. It says, my prediction failed because my starting data wasn't perfect. But the research points to a second, more insidious problem. They call it the Hawkmoth Effect.
Okay, the Hawkmoth Effect. Is this just a bigger, scarier butterfly?
It's a different kind of monster. The butterfly effect is about errors in your data. The Hawkmoth effect is about errors in your model.
So, errors in the equations themselves.
Yes. It says, my prediction failed even though I had perfect data because my mathematical understanding of the laws of physics was slightly wrong. Even if you were Laplace's demon and you knew the position of every particle, if your formula for fluid dynamics was off by 0.00001%, your prediction of the weather would still eventually fail.
That feels like an even higher wall. Because how can we ever be sure our models are perfect?
We can't. That's the point. It's called structural sensitivity. In complex systems, a tiny flaw in the architecture of your model can lead to a catastrophic failure in the output. We are always approximating reality, and chaos punishes approximation.
So just to recap, we're completely boxed in. We have computational irreducibility saying we can't fast forward the future. We have the butterfly effect saying we can never know the present perfectly enough. And we have the Hawkmoth effect saying we can never model the rules perfectly enough.
And just to really hammer the final nail in the coffin of certainty, the research brings in algorithmic information theory.
Ah, yes, Kolmogorov complexity. This one felt a bit abstract, but it's really interesting. It actually redefines what we mean by the word random.
It does. It's a beautifully elegant idea from the Soviet mathematician Andrei Kolmogorov. He asked a simple question. How do you measure the complexity of something, like a string of numbers?
My first thought would be, well, how long is it?
That's part of it. But Kolmogorov's idea was more clever. He said the complexity of a piece of information is the length of the shortest possible computer program required to generate it.
Okay, you're going to have to give me an example.
Sure. Think of the number pi. The sequence of digits goes on forever. 3.14159. It looks random, but is it complex?
I would say yes.
By Kolmogorov's definition, no, because I can write a very short computer program, a simple formula, that will generate every single digit of pi in order forever. The description is tiny compared to the output. It's compressible.
Okay, so it has low Kolmogorov complexity because it has a hidden pattern, a recipe.
Exactly. Now consider a string of numbers you get from flipping a coin 1,000,000 times. Heads, tails, tails, heads. To reproduce that exact sequence, what's the shortest program you could write?
Well, there's no pattern. You just have to write a program that says print H, print T, print T, print H for 1,000,000 lines.
Exactly. The program is just as long as the sequence itself. You can't compress it. It has no simpler description. And that, for Kolmogorov, is the definition of randomness. Randomness is incompressibility.
And how does this relate to predicting the future?
Chaotic systems are what information theorists call information generators. As they evolve, they produce new information that is, in a sense, algorithmically random. The pattern of the weather next month can't be compressed down from the pattern this month. The future contains genuine surprise that wasn't encoded in the past.
So you constantly have to be taking new measurements just to keep up. The system is always creating new complexity that your model has to account for.
It never lets you rest. It's an open, creative process, not a closed, mechanical one. And we see this reflected even in the purest of disciplines, mathematics. The research briefly touches on Gödel's incompleteness theorems and Turing's halting problem.
The ultimate mathematical walls.
They are. These aren't theories about the physical world, they are proven theorems of logic. They show that there are true statements in mathematics that can never be proven, and that there are computer programs where it is impossible to know in advance if they'll ever finish running or just run forever. There are fundamental, unknowable aspects baked into the very structure of logic itself.
So the foundations are clear. The dream of a clockwork universe is dead on multiple fronts. Physics, computation, and logic. We live in a fog. But we still have to get through the day. We have to build things, make decisions, and manage risk. And this brings us to section 2, the active debate, where science disagrees.
This is where things get really practical. The debate isn't about whether uncertainty exists, it's about how we should deal with it, especially when it comes to the big world-changing events, the crashes, the disasters, the pandemics.
And this is framed in the research as a real intellectual heavyweight match. In one corner, you have Nassim Nicholas Taleb and his idea of black swans.
And in the other corner, you have the physicist Didier Sornet and his counterproposal, Dragon Kings.
It's a fantastic debate. Let's start with Taleb, since most people have probably heard the term black swan before.
They have, but it's often misused. People use it as an excuse. A CEO misses their earnings target and says, oh, well, it was a black swan event, unforeseeable.
The ultimate get-out-of-jail-free card.
Right. But Taleb's definition is much more rigorous. A true black swan has 3 properties. First, it's an outlier. Nothing in the past pointed to its possibility. Second, it has an extreme impact. And third, after it happens, humans invent an explanation that makes it seem predictable in hindsight.
Okay, so it's prospectively unpredictable, but retrospectively explainable.
Exactly. Taleb argues these events come from a mathematical domain governed by heavy-tailed power laws. This is a key point.
Let's break that down. A normal distribution, like a bell curve, describes things like human height. Most people are clustered around the average.
Right. If you have a stadium of 50,000 people and you add the world's tallest person, the average height of the stadium barely budges. Outliers don't have much impact.
But a heavy-tailed distribution describes things like wealth or book sales.
Or stock market crashes. In that same stadium, if you're measuring wealth and Bill Gates walks in,
He single-handedly changes the average for everyone. His one data point dominates the entire system.
that's a heavy tail. One single event can be more significant than all the others combined. Taleb's argument is that history is not driven by the slow and steady, but by these massive, unpredictable, heavy-tailed shocks. World War I, the rise of the internet, the 9/11 attacks.
So what's his advice? If you can't predict them, what do?
You don't try. He says it's a fool's errand. Spending money on predictive models for black swans is like buying astrology charts. Instead, you should focus on building robustness.
Anti-fragility, he calls it.
Yes. Build systems that can take a punch without breaking or that even get stronger from shocks. If you're a banker, don't leverage your firm 100 to 1 because you know a black swan is mathematically possible, even if you don't know when. It's about survival, not prediction.
It's a very defensive, almost stoic philosophy.
Yeah.
Prepare for the worst because the worst is inevitable and unpredictable.
It is. But then Didier Sornet comes along and looks at the same data, the same historical disasters, and says, hang on a second, I don't think all of these monsters are the same species.
This is where he introduces the Dragon King. I love the name. What makes an outlier a king instead of a swan?
This is the core of the disagreement. For Taleb, a black swan is just a very rare event from the same family as all the others. It's part of that same power law distribution, just way, way out on the tail. A very rare bird, but still a bird.
Okay.
Sornet argues that a dragon king is a different beast entirely. It's a meaningful outlier. It's an event that doesn't belong to the power law at all. It's generated by a specific, identifiable mechanism.
It's not just bad luck, it's a failure of a specific part of the system.
Exactly. And that mechanism is almost always a positive feedback loop that pushes the system towards a critical point or a phase transition.
The classic example of a positive feedback loop is microphone screech, right?
A perfect analogy. The microphone picks up the sound from the speaker, amplifies it. The speaker plays the louder sound, the mic picks it up again. It spirals out of control until you get that deafening screech. That screech wasn't a random black swan event. It was the predictable result of the system's dynamics.
So Sornet is arguing that things like the 2008 financial crash were more like microphone screech than a random lightning strike.
Yes. And here is the crucial difference. Because Dragon Kings are the result of a process, a build-up to a critical point, they emit warning signs before they happen. He calls them weak signals or precursors.
This changes everything. If it's a black swan, you're helpless to predict it. If it's a Dragon King, there are clues. The ground might shake before the earthquake.
And Sornet and his group claim they can detect these precursors. In material science, before a bridge support snaps, it emits tiny acoustic signals as microcracks form. In economics, he looks for things like super exponential growth, decorated with accelerating oscillations.
When the price chart doesn't just go up, it goes vertical.
And not just vertical, but the swings around that trend get faster and faster. He argues that this is the statistical signature of a bubble, a system locked in a positive feedback loop that is mathematically unsustainable and headed for a crash.
The research has a fantastic case study on this. The U.S. economy from roughly 1982 to 2007. The period economists smugly called the Great Moderation.
This example really brings the debate to life. On the surface, for 25 years, everything looked great. Recessions were short and shallow. Inflation was under control. The mainstream view was that we had finally tamed the business cycle.
We thought we had built a crash-proof machine.
But if you apply Sornet's Dragon King lens and look under the hood, you see a completely different picture. The source material on the perpetual money machine illusion is damning.
What were the signals?
Look at the debt. The total debt to GDP ratio in the U.S. went from around $1.60 for every dollar of economic output in the early 80s to over $3.50 by 2007. The entire system was becoming massively leveraged.
We were borrowing from the future to pay for the present.
And look at the gap between productivity, wages, and consumption. For the average worker, real wages were stagnant for decades, but consumption kept rising. People were buying bigger houses, more cars, more stuff. How?
Debt, credit cards, home equity loans.
Exactly. And virtual wealth. Your 401k was going up, your house price was going up, people felt richer, so they spent more. This created the positive feedback loop. Rising asset prices fueled more borrowing, which fueled more spending, which pushed asset prices even higher.
It was microphone screech on a national scale.
It was. So when the crash came in 2008, the Black Swan camp said, this was a Six Sigma event. No one could have predicted the collapse of the subprime mortgage market. But the Dragon King camp said, we've been pointing at the super exponential growth in housing prices and debt for years. The specific trigger was unpredictable, but the crash itself was not.
This leads to a profound difference in how you should manage risk. The Black Swan approach is to be resilient. The Dragon King approach suggests you can be proactive.
And that's where we get the sandpile analogy, which is a perfect way to visualize this. It comes from the science of self-organized criticality.
It could walk us through the sand pile.
Imagine you're dropping single grains of sand one by one onto a flat surface. A cone-shaped pile starts to form. As the pile gets bigger and its slopes get steeper, you start to see little avalanches.
Right, a few grains slide down.
Eventually, the pile reaches a critical state. It's as steep as it can possibly be. Now, the next grain of sand you drop could do nothing. It could cause a tiny slide, or it could trigger a catastrophic avalanche that collapses the entire side of the pile.
And you can't know which one it will be.
That's the Black Swan view. The system naturally organizes itself into this critical state where a huge event is always possible but never predictable. So your only strategy is to build a box around your table to contain the sand when the avalanche happens. Focus on robustness.
But the Dragon King perspective would ask a different question.
It would ask, can we see the pile getting too steep? Can we monitor the system for signals that it's approaching that critical state? And if we can we intervene? Can we reach in and gently move a few grains of sand from the peak to the base to relieve the pressure?
Can we use tiny targeted interventions to prevent the catastrophic failure?
It's the difference between buying fire insurance for your house, which is the Black Swan approach, and installing a smoke detector and sprinkler system, which is the Dragon King approach. One is passive resilience, the other is active prevention.
But there's a danger there, isn't there? The research mentions the illusion of control. What if our interventions make things worse?
That's the dark side of the Dragon King idea. Think about forest fires. For decades, the policy was total suppression. Every time a small fire started, we put it out immediately.
Which sounded like a good idea.
But what it did was it allowed all the deadwood, the underbrush, the fuel, to build up on the forest floor. We suppressed all the small natural clearing fires.
So when a fire finally did get out of control,
It became an unstoppable inferno because there was decades worth of fuel ready to burn. It's possible that the Great Moderation was exactly that. By using monetary policy to suppress every small recession, every minor market correction, we allowed systemic risk and debt to build up to catastrophic levels.
So the Dragon King approach is incredibly powerful if you get it right, but you risk making the ultimate disaster even bigger if you get it wrong.
It's a high-stakes game, and that's why everyone is so desperate for better tools, for better ways to see the future, which brings us right to the bleeding edge.
It does. Section 3, Frontiers, what might change everything. Because for the first time, we're building tools that don't just compute faster, they compute differently. Let's talk about the big one, quantum computing.
The ultimate buzzword. It promises to change everything.
When you hear phrases like quantum supremacy, it's easy to think, okay, Laplace's demon is back on the table. But the reality is a lot more complicated, isn't it?
It really is. First, we need a quick refresher on what a quantum computer actually does. Your laptop, your phone, they all work with classical bits. A bit can be a 0 or a 1, a switch that's either on or off.
Binary.
A quantum computer uses qubits. And thanks to a quantum property called superposition, a qubit can be a 0, a 1, or a coherent blend of both at the same time.
It can explore multiple possibilities at once.
Exactly, and the research we looked at mentions the next step beyond that, qubits. If a bit is a two-state system, 0 or 1, a qubit is a d-state system. It could have 3, 5, 10, or more possible states.
It's like going from a light switch to a dimmer switch with infinite settings. The information density must be incredible.
It's astronomical. And the great promise of this power is that it will allow us to simulate systems that are completely dark to classical computers.
Right.
The canonical example is drug discovery.
Why is that so hard now?
Because simulating the quantum interactions of a complex protein molecule to see how a drug might bind to it is a problem of exponential complexity.
Right.
There are too many possible configurations. For a classical computer, it would take longer than the age of the universe to check them all.
But a quantum computer.
A quantum computer, because it operates on the same quantum principles as the molecule itself, could theoretically find the most stable configuration, the answer, in a matter of hours.
That's a revolution for medicine.
It absolutely is, but, and this is the crucial but for our conversation, does it kill chaos? Does it let us predict the weather for a year? Does it solve the Lyapunov exponent problem?
The sources seem pretty clear on this. The answer is no.
A definitive no. Remember, chaos is about the exponential growth of error. A quantum computer might start with a much, much smaller initial error because it can model things more precisely.
So it pushes the starting point of the two leaves closer together.
Infinitesimally close. And it can calculate their divergence much faster. But it doesn't change the fact that the river is turbulent. It doesn't make the positive Lyapunov exponent go away. The error still grows exponentially.
So what does that buy you? If you have a computer 1 trillion times more powerful, does that let you predict the weather for 1 trillion times longer?
No. That's the brutality of exponential growth. It might buy you another week, maybe. You push the prediction horizon back a little bit, but you can't eliminate it. The wall is still there. You just get a slightly better view of it before you crash into it.
So it's an incredibly powerful flashlight, but it can't turn night into day.
That's a perfect way to put it. It will solve certain types of incredibly complex but fundamentally closed problems. It won't solve open, chaotic, information-generating systems.
Okay, there's another really strange frontier mentioned in the research, quantum biology. This feels like science fiction. We think of quantum effects happening in super-cooled labs, not inside warm, messy living things.
Well, a growing field of research is suggesting that's wrong. Things like photosynthesis in plants or how birds navigate using the Earth's magnetic field might rely on quantum phenomena. And the big controversial question is, does the human brain?
Is our consciousness a quantum computer?
That's the question at the heart of convergent neuroscience. Is the brain just a classical wet computer with neurons firing like on-off switches? Or are there quantum processes like superposition and entanglement happening inside our neurons that are essential to thought and consciousness?
What would that even mean?
It's a wild idea. On one hand, it could mean that human choice is fundamentally unpredictable. If a decision you make depends on a quantum state collapsing into one reality, then even a perfect brain scan couldn't predict your choice beforehand. It could be the physical basis for free will.
But on the other hand, If we could understand those quantum processes,
We might unlock completely new ways to treat things like depression or schizophrenia. Instead of just bathing the brain in chemicals, we could design drugs that target specific quantum interactions within a single patient's neurobiology. True personalized medicine.
so again, it pushes the boundaries of what we can understand and simulate, but it might actually introduce a new layer of fundamental unpredictability into the equation.
It's a paradox. The more we learn, the more we realize how much we can't know for certain.
And that leads us to the other technological giant in the room, artificial intelligence. We're building these incredible large language models, deep neural networks. They're doing things we thought were decades away.
But they come with a massive catch.
The black box problem.
Yes. We can design the architecture of the neural network. We can choose the data we train it on. We feed it a prompt, and it gives us an astonishingly coherent answer. But if we ask it, how exactly did you arrive at that answer? It can't tell us.
The why is opaque.
It is. This is known as the performance interpretability trade-off. It's a fundamental tension. The more powerful and complex you make an AI model, the less understandable its internal reasoning becomes. A simple model, like a basic flowchart, is easy to interpret but not very smart. A massive neural net is brilliant, but its reasoning is just a set of billions of mathematical weights that have no intuitive meaning to a human.
The sources refer to this as an interpretability ceiling. Is this just a temporary technical problem, or is it another one of those fundamental walls?
The theory is that it might be fundamental. It connects back to Kolmogorov complexity. If the AI has discovered a truly complex pattern in the data, a pattern that is algorithmically incompressible, and we ask it for a simple explanation,
We're asking it to do the impossible. We're asking it to compress the incompressible.
we're essentially asking it to lie to us, to give us a simple story that makes us feel good, but that story, by definition, has to be less accurate than the complex reality the AI has perceived.
So we're building a new form of intelligence that we can't fully understand. We can predict what it will do on average, but we can't prove why it did a specific thing in a specific case.
And people are trying to work around this. The research mentions methods like proto-dash. Instead of explaining the why, it tries to explain by analogy.
So if an AI denies your loan application,
Proto-dash won't show you the math. It will search its database and say, the AI denied your application because your profile is very similar to these 5 other profiles, and all of them defaulted on their loans.
it's reasoning by precedent, like a court case.
Yes, but precedent isn't proof, it's just correlation. And this lack of true explainability becomes terrifying when we start handing over real-world power to these systems.
Absolutely. This is the perfect transition, because these aren't just academic exercises anymore. This is happening now. And that brings us to Section 4, Implications. Ethics, Economics, Society.
The rubber is meeting the road, and there are a lot of crashes.
Let's start with the economy. Algorithmic trading. We've taken the slow, human-driven stock market and turned it into a high-frequency battleground for bots.
And the quintessential example of what can go wrong is the flash crash of May 6, 2010.
I remember watching this happen live on the news. The market just evaporated.
The Dow Jones Industrial Average plunged almost 1,000 points, a nearly 9% drop in about 5 minutes. $1 trillion of market value vanished into thin air. And then, just as mysteriously, it bounced back 20 minutes later.
The scariest part was that there was no reason. No war was declared, no major company went bankrupt. It just happened.
It was a purely internal system failure, a chaotic feedback loop between different trading algorithms. A large institutional seller used an automated algorithm to sell a huge block of futures contracts. This triggered other algorithms' stop-loss orders, which created more selling pressure, which in turn triggered momentum-based algorithms to start short selling.
A digital avalanche. Algorithms reacting to other algorithms at speeds no human could possibly track or intervene in.
We've created a system that is a perfect breeding ground for Dragon Kings. We have high-speed, positive feedback loops hardwired into the core of our financial infrastructure. We've built an instability engine.
And we're taking that same logic and applying it to society. Which brings us to predictive policing. This one is deeply troubling.
It's a textbook case of a runaway feedback loop creating and reinforcing systemic bias.
Let's walk through the mechanism very carefully, because it shows how objective math can produce deeply unjust outcomes.
Okay, step 1. An algorithm is designed to predict where crime is most likely to occur so police can patrol more efficiently. To do this, it's fed historical crime data.
And that historical data is already biased. It reflects where police have patrolled in the past and which communities have historically been over-policed.
Precisely. So the algorithm looks at the data and says, there are a lot of arrests in neighborhood A. Therefore, neighborhood A is a high crime area. Send more police to neighborhood A.
Step 2. The police follow the algorithm's advice. They flood neighborhood A, and because there's a heavy police presence, they see more crime. They make more arrests, often for minor, low-level offenses that would go unnoticed in other neighborhoods.
Step 3. This new arrest data is fed back into the algorithm as proof of its success. The algorithm says, see, I told you neighborhood A was a crime hotspot. My prediction was correct. Send even more police.
Meanwhile, neighborhood B could have just as much crime or even more serious crime, but because there's no police presence, there are no arrests, and the data says it's perfectly safe.
The model becomes a self-fulfilling prophecy. It doesn't discover reality. It creates it. And because of the black box problem, when citizens complain about being over-policed, the department can hold up its hands and say, we're not biased. We're just following the data. It's objective math.
It's what some call bias laundering. You take a biased human process and run it through a complex machine to make it look impartial.
And we see the same pattern in AI for hiring. If you train a model on 20 years of a company's hiring decisions, and that company has historically only hired men from Ivy League schools for leadership roles.
The AI will learn that being a man who went to Harvard is a key qualification for the job.
And it will systematically downgrade qualified female candidates or candidates from state schools, not because of any explicit rule, but because it has learned to replicate the hidden biases in the historical data.
It's horrifying, but let's take it to the ultimate implication. Autonomous warfare.
Lethal autonomous weapon systems, law WASs.
The research lays out a spectrum of control. Human in the loop means a person has to pull the trigger. Human on the loop means the machine can act on its own, but a human can override it.
But the frontier we are approaching is human out of the loop, or minds off, as the source calls it. The machine identifies, tracks, and engages a target without any direct human approval.
There's a really stark philosophical debate in the source material about human dignity. Is there something uniquely awful about being killed by a machine?
My gut reaction, and I think most people's, is yes. To be hunted and executed by a piece of software feels like a profound violation of what it means to be human.
But the counterargument presented is coldly pragmatic. It says the victim doesn't care. A Hellfire missile from a drone piloted by a human in a bunker thousands of miles away is just as lethal as one fired by an AI. Dead is dead.
And it goes further. It argues that human soldiers are flawed. They get scared, they get angry, they want revenge, they commit war crimes. A machine feels none of that. It just followed its programming. In theory, it could be a more ethical soldier.
But it also has no capacity for mercy. It can't recognize a surrendering soldier who isn't behaving exactly as the programmers predicted. It can't make a judgment call based on context or compassion.
And what happens when its programming has a bug? A black swan error in its targeting algorithm, or a Dragon King feedback loop where it misidentifies a school bus as a tank convoy.
A massacre occurs, and there's no one to hold responsible. You can't put an algorithm on trial for war crimes. It creates an accountability vacuum.
It feels like every technological solution we create to manage uncertainty just ends up creating a new, more complex, and potentially more dangerous form of uncertainty. We swap the devil we know for the devil we don't.
And we can't forget the physical cost of all this.
Yeah.
The environmental impact of our quest for prediction is enormous.
It's a point that's often completely ignored. The energy consumption required to train one of these massive AI models is staggering. We're talking about a carbon footprint equivalent to hundreds of transatlantic flights.
We're burning fossil fuels to create digital crystal balls.
And then there's the hardware itself, the e-waste. Our entire tech industry is built on a model of planned obsolescence. Your smartphone is designed to be replaced in 2 years. This creates literal mountains of toxic electronic waste. We are stripping the earth of its resources to build machines to predict the future, while the very act of building them is actively destroying that future.
That is the ultimate tragic irony.
It really is.
We have covered so much ground. From the death of Laplace's elegant clockwork dream to the messy reality of chaos, the fight between swans and dragons, the promise and peril of AI, and the life and death consequences of these ideas. My initial feeling of dread hasn't completely vanished, but it feels, more focused now.
That's a good place to be.
So what's the takeaway? For everyone listening, how do we live in this world of structural, unavoidable uncertainty?
I think we have to come back to that phrase we started with, epistemic opacity.
We have to accept the fog.
We have to accept the fog. We have to internalize, truly internalize, that the universe is not a puzzle to be solved. It's not transparent to us. We will never have the perfect data. We will never have the perfect model. We are not and will never be Laplace's demon.
That sounds almost like a counsel of despair.
I actually think it's the opposite. I think it's incredibly liberating. Because once you let go of the fantasy of perfect prediction and control, you can stop wasting energy on the impossible. Your focus shifts
It shifts away from predicting control and towards what?
towards monitor, adapt, and build resilience. You stop trying to predict the exact grain of sand that will cause the avalanche. Instead, you build your life, your company, your society with the assumption that avalanches will happen.
We build the box around the sand pile.
You build the box, you diversify your investments, you build social safety nets, you demand human oversight for powerful algorithms. You stop searching for certainty and start learning how to dance with uncertainty. It requires a kind of radical humility.
The humility to admit we are navigating in a fog. And the only way forward is to take one careful step at a time, keeping our senses open for the tremors in the ground.
That's it. The exploration of predictive limits reveals a universe that is fundamentally epistemically opaque. That's the key line from all this research.
You must learn to navigate a world where the only way to find out what the future holds is to live it, one step at a time.
Well said.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.